Neurips 2024, part 16. Today we're discussing a paper and a presentation by Kaiming. The paper is about representation learning, about unsupervised representation learning, and the presentation is just a formal presentation at a MIT machine learning boot camp where he talks about representation learning from a conceptual perspective. And I think it's worth revisiting the idea of representation learning for several reasons. First, I think it's, like he says, it's the fundamental underlying idea of deep learning as we know it. So what we're really trying to do is take high-dimensional data such as pixels, waveforms, text, and turn it into a latent space, into a compressed database that is machine readable and that inference can be done because the representations of the high-dimensional data. So for example, in image recognition, we have pixels coming in, pixels which have, 256 times 256 times 3, and then we have 2 to the power of that in terms of possibilities of zeros and ones that could represent those pixels. And clearly that is hugely dimensional, and we can't make sense out of that, right? So we have to sort of have a higher level structure. That's what Kaiming calls representation, and then learn from that. I mean, that's what we humans do, right? When we take a chair, we look at a chair not from a atom perspective. We don't look at the individual atoms of the chair, or we don't look at all the relationships between the chair and the rest of the environment. We kind of have a representation of the chair, which allows us to use the chair, to sit on it, or to avoid the chair if it falls down, or things like that. So that's so again, representation learning is the core idea here, and I think Kaiming has been on this podcast. He's been mentioned several times because he really is one of those rare individuals that can combine complex ideas, convey them in simple forms, and also always inspire. This is not even on podcast. It's February 12, 2025. This is Krim Delco. For the year, we are down 15.5%. The market is up 2.7%. We're outperforming by 18.2%. The drawdown in Tesla has been flagged already, and I think that's why we're down. So I don't want to discuss a little bit more. I don't want to discuss more, but I just want to mention one important thing that happened yesterday, and that was the press conference that Musk gave with Trump together about Doge. And I think the press conference is very powerful in several ways. Fundamentally, what Musk is trying to do is, of course, cut corruption, cut waste, reduce the government deficit. And I think he does it in a human way, and that's important. I think the whole administration, from whether it's J.D. Vance, whether it's Trump, whether it's Musk, and hopefully all the other big figures that are already part of the administration, like Pete Haskett, or the new ones like Tulsi, and hopefully soon RFK. All of them have a certain human factor to it, that they're really trying to do the right thing, and I think that's very positive. In terms of the markets, I think what's concerning us is definitely the rising of the gold price, which is signaling inflation, and that's not a good thing. Now, of course, Doge is fighting that, so we're hopefully on the verge of reversing that. But that is, in my opinion, the most concerning thing in the last couple of months is the rise in the gold price. That's I guess it's a tug of war between gold and the S&P. One will win. Either we're going to have continuous money printing and gold will go through the roof, or we have Doge winning, and then we have gold not going to the roof, and a massive real growth, which means a high S&P 500. So now let's talk about Kaiming He's. First, let's talk about the presentation and then the papers. The presentation is, and the reason I want to do the presentation first is because it's an intro. It's a boot camp about machine learning. So it teaches you basically what machine learning is all about. And I think there's two fundamental concepts. One is the sort of history of machine learning, which he depicts really well. And then the other is the importance of initialization and normalization. I'm going to talk about both of these things. So let's talk about the history first. So Kaiming basically gives you a history of machine learning from the perspective of representation learning. So he mentions a very important fact that the International Conference of Representation Learning, ICRL, actually was started by Jan LeCun and Joshua Bengio. I think that's true. I don't know if I have to fact check that. But the point is they wanted to have a representation learning conference because computer vision and neural nets and all those things were hijacked by the symbolic logic people and the expert system types people and all these people who wanted hard-coded knowledge, who wanted logic, who wanted linguistic knowledge compressed into AI systems, and that just didn't work. What representation learning really means is that in the context of image recognition is that you take a very high-dimensional bunch of pixels, and then you try to learn from those high-dimensional pixels. You try to learn something, right? Whatever it is, and let's call that representation. You try to learn how is this thing represented, and then with that representation, we can do, for example, classification. So that's how it started, right? ImageNet, the big breakthrough with AlexNet was that we were able to classify cats and dogs. But of course, it goes on. We, for example, also want to do image generation. That's what we're doing lately, and it's the same idea, right? We've learned some sort of representation of what a cat is. What's the catness of cat? What's the dogness of dog? And then we can reproduce dogs once we have access to that type of information. So the history is really, in a nutshell, three big ideas: recurrent neural nets, convolutional neural nets, and transformers. They're kind of the same thing. They're just the next evolution. So RNNs, they take information, they learn something, and then they take new information and they update the learning. So that's kind of like a Kalman filter idea from systems control, where you have a certain, let's say, a system that should react to input in a certain way. But with new input, you also change that reaction function. That's what recurrent neural nets are. Convolutional neural nets are similar, but they kind of attend a little bit more than just the new information changes the existing filter. Convolutional neural nets also try to take advantage of symmetries. Convolutional neural nets have this beautiful property that you can have you can have changes in the input that also change the output in a sort of symmetric way. Again, you take advantage of symmetries. For example, if you have if you want to identify letters, which is again one of the early endeavors of the neural net community, was to identify handwriting. So if you have the letter A, you don't have to really attend to every possible pixel on that piece of paper. All you need is understand when the symmetries break. In other words, when there's a line, when otherwise there isn't, right? And that's where you start learning, okay, this might be an A, the lines that represent an A. And then the transformers, the next evolution, which is a same idea, actually. It's recurring in the sense that we have new information updating the old information. The only difference is that the representation of the transformer now has this cross-attention mechanism. So basically, each node attends to each other node. So there's a lot more interaction, and it's another really beautiful thing is parallelizable. You can use GPUs to train it. So that's kind of the big idea. The other big idea that Kaiming discusses is the importance of normalization. Now, think about it this way. If you want to learn end-to-end from data, right? You don't want to have catastrophic forgetting. You don't want to have weight explosion, or you don't want to have weight destruction. In other words, you don't want certain, okay, if you have, let's say, if you're looking at the sunset, you're on the beach, you're looking at the sunset, and then there is a plane crossing. You don't want that plane to distort the whole picture, right? And the way you do that is you normalize. So you make sure that all the system is learning is kind of relationships between information and not the absolute level of information, because certain absolute levels of information could distort the whole picture. So that's really fundamentally what deep learning still is. That's how it started a long time ago. That's how it got proliferated through the AlexNet times and then the transformer times. That's where we are today, and I think that's where we're going forward. Now, his most recent paper published at Neurips is actually about representation learning, and it's about unsupervised representation learning. And the paper, by the way, all the links are in the show notes, the paper and this presentation that I was talking about. So the paper, what is the paper trying to do? The paper is trying to sort of separate the representation function from the actual task of the neural net, whether it's image recognition, image generation, classification. So what it does is it learns how to represent stuff. That's what it does. So it's a separate algorithm that learns how to represent. So in other words, the algorithm learns that when it's exposed to cats, that it's supposed to represent cats in a certain way. So it learns how to represent stuff. It doesn't learn what cats are. That's the next step. It just learns how to represent. So in other words, it learns, let's say, that it's important when it's exposed to pixels to generate certain representations around edges. It's important to generate certain representations around maybe contrasts or things along those lines. Again, it's actually hard to put it in words what exactly it's learning, because that's the whole black box concept of machine learning. But I think that's a feature, not a bug, because that's exactly the reason why we have unsupervised representation. It's because we don't quite know what catness actually means, and we don't know what kind of representation is ideal for something that represents cats. So why don't we just feed the thing a lot of data and let it learn? Now, the way it learns, there's some technicalities in the paper. It's using a very simple diffusion network to actually learn representations. Once it learns the representation, then you can go from there and then, let's say, use it for classification or image generation. So I think, to summarize, Kaiming is really all about representation. He's the one who also wants to really get to, I guess, put image recognition and computer vision take it to the next level, I guess, to simplify. Because I think what he's trying to do is forcefully and intellectually and inspirationally always put us sort of a little bit on the back here, make us feel uncomfortable. Like, look, we're not there yet, right? There's still a lot to learn. Unsupervised representation learning can really open up new doors, for example, in computer vision for robotics, because the holy grail is to see, understand nature. That's really what intelligence is all about. And it applies to robotics as much as it applies to humans. So we need to have better ways to represent nature. We need to have better ways to understand the difference between a woman and a statue that represents a woman, and things along those lines. So to summarize, I think Kaiming's presentation, again, very sort of fundamental, I think worth looking at, and his work on representation, I think, in my opinion, opens the doors for new ways to think about the problem of computer vision, and that to me is computer vision is definitely one of the main steps, other than simulation, towards a more real-world AI. I think the last thing I want to say, this is just a comment, and it's very interesting. Like, he mentioned something on a side note, which I paid attention to, and that is that in the early days of pre-AlexNet, so when LeCun and Hinton and Benjo and all the others were working on neural nets, Andrew Ng here at Stanford, what they were really also doing, which is important, is they were starting to use GPUs for their purposes. And I think it's interesting to think about that. Like, for example, today we're exposed to quantum computing, right? And I think it would be interesting to think about certain problems in AI, which I think they exist, that could be better solved with quantum computers. So sometimes it's really useful to really go all the way up the stack, right? All the way up the stack, upstream, or whatever you want to call it, right? Actually, that would be down the stack. And think about the math, for example, the computational theory that underlies a world in which quantum physics actually can be used for computation. And then think about how that can be used for representational learning in particular, and more generally for AI. I think that's an interesting thought, and I think it's going to happen. It's going to happen sooner than we think. So technologies can have massive impact, particularly when they compound like that. When, let's say, quantum computing compounds with AI, we can really, really have very interesting outcomes. Thank you.